Yeah, hi. Good evening, everyone. I am Shubhanu Haldar. I am a PhD student at IIT Delhi. Today we will be discussing on the uh, week 8 of Design Analysis and Algorithm course. So, as like the previous weeks, we will be discussing the questions on linear programming, LP modeling, production planning, and all, and we will be try to solve some questions on it. Okay. So let's start our exercises. Okay, so our first question is on 3 sat and 2 sat problem. Okay, so as we discuss, please, if you are able to solve the questions, so please please try to write your answer in the chat box, and then we'll be seeing how we solve these questions. So if you see if you try to solve the quizzes and all, and whenever you will uh, get some questions on these chapters, so so sir, I have not done week 8. Okay, so if you have not done week 8 yet, if you have not seen the videos yet, this is fine, because in class sir have told you about other methods like linear programming and all. And there are two things basically: one is linear programming and network flows, and one is interactability. Okay, so we will be try to see that what we can discuss. So till this week, we have seen that there are so many problems. We have seen so many algorithms, okay, and we have solved so many problems till now. Okay, so basically we have some problems we have solved using the algorithm. Okay, so there are two types of. So so our question was this, basically 3 sat and 2 sat. Okay, so first we will be try to discover that why we are. I think I am back. Okay, so we'll be trying to discover that why we are uh, we will be solving this problem. Okay, so some problems in algorithm can be solvable, and some problems are not solvable in real life also. That some problem we have, these are not solvable. Okay, so there are two types of problems. Okay, one is decidable and one is undecidable. So what does decidable means? So decidable means that for this kind of problem, algorithm exists. Okay, and for undecidable problem, no algorithm exists. Okay, and then this decidable problem. So now we these are classified. Okay, decidable and undecidable. Okay, now decidable problem also has two classification. One is tractable and another is intractable. Okay, so what does it means by tractable problem? Okay, tractable means if there exists at least one polynomial bound algorithm. Okay, so we know that one problem can be solved using many ways. Okay, so at least, so we have seen in past, when in our first chapter we have seen what is big omega and what is theta. Okay, so basically one problem can be solved in many ways. So at least if, so tractable problem are if at least one polynomial bound algorithm exists. Okay, then, so polynomial bound means, so it can be solved in order of n to the power k. Fine. Okay. Now, what is interactable? Interactable means if a problem is not tractable, then it is interactable. So, what are interactable problems? Like n to the power log n, okay, or n to the power cn, okay, or kn, whatever you can say. Fine. Now, now there are two types of problem. Okay, so so decidable and undecidable, where algorithm exists and algorithm doesn't exist, you know. Now, for decidable problem, we have two types. One is optimization based problem and one is decision based problem. Okay, so one is so this optimization based problem are you have already solved that. One is traveling salesman's 01 knapsack. Okay, these are optimization based algorithm. Longest common subsequence. Okay, these are optimization based algorithm. And what is decision problem? So if there exist any SP covering, so if so basically if there are any SP covering all vertices of length at most k, so if there is, so decision means yes or no. Okay, so if someone asks you a question, is there any solution whose profit is at least k? Okay, so is there any solution any subsequence where the length is at least k? So you have solved the longest common subsequence problem. So, okay, you know what is longest common subsequence. So if someone asks you, so basically decision means yes no type question. Okay, so so some terminology we see basically for minimizing problem. We see at most. Okay, for maximizing problem, what do we see? We see at least. Okay, for every optimization problem there is a decision problem. Okay, so if optimization problem order of optimization problem is what is order of n to the power k is easy, then decision problem is also easy. So basically, so this is the thing that for every optimization problem basically this happens. So this is optimization and this is decision. Okay, so for every optimization problem, so basically optimization will give you a value and decision will give you yes no answer. So decision is of course a big thing. Okay, so that's why. Fine. Now if optimization problem is easy, so if optimization is easy, okay, so decision is also easy. Fine. Now what is so this is important that one thing you do. One is P and NP. Okay, question come from these two only. Okay, P and NP. So P, what is P? So P is set of all decision problem for which there is a polynomial time algorithm to solve this problem. Okay, so P is basically set of all decision problem, not all optimization problem. Okay, okay, and what is NP? And what is NP? NP is a set of all decision problem for which there is a polynomial time verification. Okay, So you got the idea of what is P and NP, fine. So mm, so basically what happens that if you see it graphically, so this is P, this is NP, okay. Intractable, this is tractable, fine. Okay, so I think you got the idea that what is tractable, non-tractable, P and NP. Okay, so basically, if I say that P is easily solved or quickly solved, okay, P is easily solved or quickly solved. So you got the answer here. Now what is NP? NP is easily verified or quickly verified. Fine. Now see that how this works. That what is three side and two side. So what is a set? Now okay. Now what is set? Uh, so basically set means that it is basically used for Boolean satisfiability solvers. Okay, so uh, so you have given a Boolean logic or formula. Okay, so like f is equal to a or b and a dash or b dash or c. Okay, so this means this means that uh, so this means or this means and, fine. Okay, and this means not, fine. So find a variable assignment such that the formula evaluates to true or prove that no such assignment exists. Okay, so what is your answer? So you have to find a variable assignment. Okay, so you have to find that what should be the value of a, what will be value of a, or what should be value of b, or what should be value of c, such that if give you a true answer. Okay, so f is equal to, what should be value of f such that f is equal to true. Okay, so you have to find a, b and c such that f become true. Okay, or prove that no such assignment exists. Okay, now we have how many variables? We have three variables, a, b and c, fine. So for n variables there are 2 to the power n possible truth assignment. Okay, so now if you see, now for a have 2 assignments, one is 0, one is 1, fine. Now b have, now b have how many assignment? 0, 1, 0, 1, fine. Now c have, c have also 2 assignments, 0, 0. I think you are getting this, like, sir, कोई आया है, एक बार खोल लो. So I think you know this, like so basically if you have three variable, okay, so you have 3 types of assignment. Okay, like 0, you can assign 0 here, you can assign 1 here. Okay, so these are the problem. Okay, so for n variable you have 2 to the power n possible truth assignment to be checked. Okay, why 2 to the power n? Because for each variable you have two options, one is 0 and one is 1. Okay, so first establish our NP complete problem. Okay, so how should we check this? So given we have given a boolean formula here like f, fine. So what is here, like, so we have first so this is basically what we are doing. It is boolean formula semantics. Okay, so given boolean formula f, so we have given a boolean formula. Okay, now what we have to do, that and then interpolation m. Okay, boolean formula f, interpolation m is given. Okay, we say interpolation means basically a function y is equal to fx like that. Okay, we say m satisfies f. Okay, so this is the point. We say m satisfies f when, like, so what is m and what is f? So f is here a or b and a dash or b dash or c. And what is m? M is how you will start this one. Will this, if you assign to true to this variable a, or true to this variable b, or true false to this variable c, will this m1 satisfy f? So our question is, so if you check that this is true, true or true, now this is false and this is false and this is false, so this will give you a false and this will give you a true. So true and false, your answer will be false ultimately. Okay, so this m1 will not satisfy f. Okay, now is f satisfiable? Like, now the question is, now question to it. So why we are doing this? So you know that we have two questions. One is P, one is it is easily solved, and one is easily verified. So we have checked that this is not solvable. Okay, so now we are checking, we cannot solve like this. Okay, so we have to check with 2 to the power 3, like 8 possibilities we have to check. Okay, so what happens that now this question is f satisfiable? Basically, does there exist any m such that m satisfies a? Okay, so this is the question. So as we have a very low set, only 8, we can check that if we take m2 as, if we initialize as a2, b2 and c also 2, then we can see that this f is equal to 2. Okay, so this is satisfiable. So SAT solvers, so basically the question is about SAT. Okay, so these are the SAT solvers. So SAT solvers can automatically find a satisfying interpretation, okay, if there exists. Okay, so we have basically two settings. One setting is to solve the problem, and one setting is to give you an answer which will say that, okay, for this at least for any of the option, any one option is correct. Okay. I think you got the idea that what is basically what is said doing. Okay. Now, okay. So the question is 3 set and 2 set. So you know what is 3 set? 3 set mean we have 3 variable ABC, and 2 set mean we have 2 variable like W and X. Okay, or X and Y. Fine. Now the question is both in P, both in NP complete and P respectively, undecidable and NP complete respectively. So please try to solve the question. I have tried to give you a basic sense of what is P. P is intractable. What is NP? Okay. NP, what is P, what is NP, and what is 3 set and what is 2 set. Now try to solve the question. So if anyone can solve this question, anything you can like put in the chat box. So basically, what is happening here? Like I am. So cannot solve the question. Okay, please. If you can listen that what is happening, that so this is Boolean. Set means Boolean satisfiability problem. Okay. Let me delete all the things. Okay. So what is happening? That so this is set means Boolean satisfiability problem. Fine. Now this is a This is a decision problem. Okay. So we have seen that we have two type of problem. One is optimization problem and one is decision problem. So in which category SAT falls? So SAT is a decision problem. Okay. Now, whose instances is a Boolean expression written using only and or not or variables and parentheses. Okay. So what we use for this SAT problem? We use and not or variables and parentheses. Okay, you can see here. Okay, variables, these are variables, these are logics, and or not. Okay, and these are parentheses. Okay, now the problem is given in the expression. Is there some assignment of true and false values to the variables that will make the entire expression true? So what is our goal? Our goal is to make f is equal to true. The entire how will you assign your variables such that your entire expression become true? So a formula of propositional logic is said to be satisfactory if logical values can be assigned to its variable to make the formula true. Okay. So 3-sat and 2-sat are very special cases of k satisfiability problem or simply satisfiability problem, when each clause contains exactly k is equal to 3 and k is equal to 2 literals respectively. So 2-sat is a P while 3-sat is a NP complete. So this one is so 2-sat is a P and 3-sat is a NP complete. Okay. So this answer is correct. Okay, C option, because 2-sat means you have only two variables. Okay, so for only two variables the checks are very easy, so you can check in polynomial time. But if you have three, so you have 2 to the power n time you need. Okay, so this is not a polynomial time algorithm. So what is happening? So this is a NP type of problem. Okay, so this option is correct. NP 2-sat is P and 3-sat is NP. Got it? Now this is the question about which of the following is true about NP complete and NP hard problem. Okay. So how this NP hard concept came here? So we'll be try to see that thing. Okay. So means case. Okay. So you have already seen the answer. That is not our goal. So to find the answer is not our goal. So our goal is to how to solve this problem. Okay. So we have basically two problems. Problem A. Okay, what does problem A says? Problem A says that, okay, given n number of Boolean variables, like x1, x2 to xn, so it has two options, 0 or 1, 0 or 1. Are you getting it? So these are Boolean variables. So Boolean variables means it has only two options, one is 0 and one is 1. Okay. Now so basically now the question is, does at least one variable have the true value? So this is the problem. So how many instances you have? You have 4 instances. Okay, like true, false, false, true. Okay, so now the answer will be, what will be your answer? Your answer will be yes. Okay, because you have at least one true value. Okay, now we have a given problem B. Okay, so given n integers, like I1 to In. Okay, and maximum of I1 to In greater than 0. Okay, okay, so the question is, so this is the question. Okay, so is maximum of this integer is greater than 0 or not? So the example is basically like this. So you have minus 30, minus 50, 20, 0. Okay, so what will be your answer? Your answer will be yes, because at maximum will be 20, so 20 is greater than 0. Okay, that's why your answer will be yes. Now we know, so we have two problem now. So what is our job? Our job is to convert problem A to problem B. So you have seen two problems, this one and this one. Now what is our goal? Our goal is to convert problem A to problem B. Got it? A to B. Fine. So what is A? A is basically this one, like true, false, and this was your boolean thing. Fine. So answer to the problem A is yes if answer of the problem B is yes. Got it? So basically, what we have to do? We have to just scan once, and that will happen in polynomial term. Got it? Now, so you have here you have learned how to convert one problem to another problem. Okay. Now, what is NP hard? So NP hard is if every problem in NP can be polynomial time reducible to a problem A. Okay, so you have seen that how you can how this problem is polynomial time reducible. Okay, so what is NP hard? NP hard is if every problem in NP can be polynomial time reducible to problem B. Okay. Or you can say so if every problem in NP can be polynomial time reducible to a problem A. Then A is called NP hard. Okay. So if A could be solved in polynomial time, then every problem in NP is P, is that polynomial time solvable. And what is NP complete? A problem is said to be NP complete if it is NP and NP hard. So what is NP complete? NP complete will be if this is NP plus if it is NP hard. Okay. So how this will this it will look like? So it will look like, so this is P, so this is the NP, this is NP complete, and this is NP hard. Got it? So you got the idea which is NP, NP complete, NP hard and P. Now try to solve this question, that which of the following is true about NP hard and NP complete. So if we want to prove that a problem X is NP hard, we take a known NP hard problem Y and reduce Y to X. Yes, we have seen that how we are interchanging problem A and problem B. Okay, so this is true. If first problem that was proved as NP complete was the circuit satisfiability problem, yes, it is also true. Okay, so I'll show you that how circuit satisfiability problem and these are well known. And if NP complete is a subset of NP hard, fine. So basically all of the are true. So NP complete is a subset of NP hard. So NP complete is a subset of NP hard. Fine, this is true. So now try to solve this question. So this was your question. So please try to solve this one when I am writing this. uh, so so if I see that if we can either use BFS or DFS to find whether there is a cycle in an undirected graph. So you know what is undirected graph. So you can use BFS or DFS to find a cycle like this. Okay. So for example, see DFS based implementation to see the direct cycle in a undirected graph. Okay. So the time complexity is order of V plus A. Okay. So using DFS or BFS, time complexity is order of V plus E. Okay. Which is, so this is polynomial. Okay. Now, so this is saying that the problem of determining whether there exists a cycle in an undirected graph. So how you will do? You will use DFS, or you will be using DFS. Okay. So you know that algorithm time complexity of DFS, BFS, or W plus is, it is polynomial. So determining whether there is a cycle or finding there is a cycle, you need order of V plus E time, which is polynomial time algorithm. Fine. So this is a P. So polynomial time algorithm exists mean this is P. Okay. Now the problem of determining whether there exists a cycle in an undirected graph is NP. So is it a NP problem? So if a problem is in P, then it is definitely in NP. So can be verified in polynomial time. So you have seen that if it is in P, so P is basically inside NP. So if one problem is in P, it definitely will be in NP. If it is in P, so NP is outside. Okay, so it is in P, definitely it will be in NP. So this is also true. Okay, now 3 is saying if a problem is a NP complete problem, there exists a non-deterministic polynomial time algorithm to solve A. Okay, so you know what is NP complete. So this is a NP complete problem. So if a problem is NP complete means NP hard plus, I have written there. So it is NP plus NP hard. Okay. So NP hard means we have a problem, we can change it from A to B. Okay. If so, you know what is NP hard. NP hard means if every problem in NP can be polynomial time at the reducible to a problem A, then A is called NP hard. Okay. So we have problem of finding if there exists a cycle in an undirected graph. So it is NP and this is NP hard, and this is NP complete also, because this problem is NP, this is NP hard. So if you combine this, you will find this is NP complete. Okay. So these all 1, 2, 3 are true. Fine. Now the question is this one, that assuming P not is equal to NP, which of the following is true? Yeah. So this is the answer that, so our answer is basically this one, np complete is equal to p. Why? That there is answer is b, no np complete problem can be solved in polynomial time, because if np complete problem can be solved in polynomial time, then all np problem can be solved in polynomial time. If that is the case, then np and p set became same, which contradicts the given condition. Okay, so this is our option. So please try to solve the next question. Hi Ravi. So are you talking about this diagram, like this one? This one? अच्छा अच्छा अच्छा, I got it, I got it. Is it? So I didn't see this diagram in any book, but this is this is very helpful for you. This will be a very handy thing. Okay, so you got the diagram. Okay, now, okay, so you have seen the diagram. Okay, now this is saying that assuming P is not is equal to NP. Okay, P not is equal to NP. Okay, so uh, which is of the which of the following is true? Okay, so you have seen that this is P and this is NP. Okay, so this is the first basic thing you have seen here, that one is P, one is NP. Okay, fine. So now, so this is fine. Yeah. So now what we have? We have NP complete and NP hard. Fine. Now it says that P not is equal to NP. So P is not in this set. So P is not here. So P is somewhere outside. Okay. So uh, now what is true? So if one NP complete can be solved in polynomial time, okay, so then all NP complete, all, like if, so NP complete so here it is say that where P should be, so P should be here or P should be here. Okay, so it says that P not is equal to NP, so P cannot be here, P cannot be in this position. Okay, okay, so where P should be? P should be here or P should be here. So now it says that if one NP complete problem can be solved in polynomial time, okay, this problem can be solved in polynomial time, then all NP problems can be solved in polynomial time. Okay, so you know that NP problem cannot be solved in polynomial time, that's why it is in NP. And what is NP complete? So do you remember that what is this? This is NP complete problem. NP complete means which is NP and NP hard. So what NP hard says? NP hard says that there is a if you have a problem and you can convert it to a problem B, and if B is polynomial time solvable, then your A will also be polynomial time solvable, and your A should be NP hard. Got it? So so uh, so if one NP complete problem can be solved in polynomial time, so if it is can be it can be solved in polynomial time, okay, then all NP problems can be solved in polynomial time. If this problem can be solved in polynomial time, so this will also be solved in polynomial time. If this that is the case, then NP and P set become same, which contradicts the given condition. If this is the case, then NP is equal to P, because it is in polynomial time. Then which contradicts the, so this contradicts the given condition. Okay, so if NP complete is equal to P, then this will contradict the given condition. Okay, so otherwise if this is NP, then it is true. If this is NP hard is equal to NP, then it is true. If P is equal to NP complete, then also it is true. Okay, only for this condition, this P not is equal to NP will not be satisfied. Yes, that is the question, that this option B will violate P not is equal to NP. Like other options, if you see that other, if there is other option, you take other options, so other options will not violate the other option will not violate this condition. Okay, only this option, only the option B will violate the condition P is equal to NP. Okay, so I think the question is like little bit unclear, like my motive was not clear here, so that's why there is a problem. I think you got it now. So please try to solve this one.
अभी चेक कर लूँगा, चल रहा है।
चल रहा है कौन सा चल रहा है?
सो लगभग 10,000 पे मैं अब HCC के पैरामीटर्स ढूंढ रहा हूँ और 5,000 पे वो ONL वाला रन कर रहा हूँ।
Done.
तो मतलब सी ट्रांसपोज सी का तो हो गया, अभी वो वाला रन कर रहा हूँ M इक्वल टू L वाला।
ठीक है, वो टाइमिंग भी लिखते लिखते जाना।
टाइमिंग से मैं कल पे दोबारा निकल लूँगा टाइम के लिए, सारे टाइम कंसिस्टेंट हो जाएंगे।
ठीक है। Okay, so let's check the answer of this question. Okay. So it is saying that if S be a NP complete problem, S is equal to NP complete, okay, and Q and R be two other problem not known to be in NP. So Q and R not known, it is not known to be in NP. So Q is a polynomial time algorithm. So what Q no? Q is equal to P. Okay. So which is reducible to S and S is polynomial time reducible to R. So Q is polynomial time reducible to S and S is polynomial time reducible to R. Okay. Which of the following statement is true? Okay. So if you remember the uh, the definitions of all the NP complete and all the other problems, so you will be correctly solve this one. Okay, so this is not known that Q and R is in NP. Okay, so S is NP complete. Okay, so let's design our diagram again. So this is P, this is NP, this is NP hard, and this is NPC. Okay, so where where you are lacking that. So what is NP hard? So what is NP hard? So this is not clear to you. So if so if every problem in NP, so this is NP hard, you see here. So this is NP hard. So if so NP hard is only this much. Okay. So it is saying that if every problem in NP is polynomial time reducible to a problem A. Okay. So so if each problem, so x y z, there are three problems, x y z w. Okay, w is in P, x in NP, y in NP, and z in NP. Okay, so if all w x y z all are np hard, only w is a p. Okay, so if if every problem in np can be polynomial time reducible to a problem a, then problem A, then A is called the NP hard problem. Okay. So if A could be solved in polynomial time, then every problem in NP is P. Okay, is that polynomial time solvable? Okay. So basically, if here it happens that every problem in NP can be polynomial time reducible to a problem A. So X can be reduced to a Y. So this is reduced. Okay. So X is bigger, A is lower. Okay, A. So I W Z A. Then A is NP hard, not X is NP hard. X, what is X? X will be NP or P. Got it? So NP hard is a subset of NP. Got it? Now our question was that, so, and S is NP complete. Okay. So now like Shreya is saying B, option B. Okay, fine. So let's how should I start? We start by checking the option R is NP complete or not. Okay. So so uh, R is NP complete or not? R is not. So R is in NP. So what do we know about R? We know about R that R is S is polynomial time reducible to R. Okay. Q and R not in NP. Okay. R is not in NP. So R not in NP. Okay. And NP complete problem has to be in both NP and NP hard. Sorry. So this is so 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 this is NP complete. Okay. So NP complete problem. So NP complete problem must be in NP complete problem must be in NP hard and NP. Okay. So what is the reason? If you see the reason here, so R is NPC. It is saying that R is here. R is NPC, but R not in NP. It is already defined that R problem not known to be in NP. So we don't know that R is in NP. So how could we conclude that it is a NP complete? Because to be NP complete, to be NPC, you both have NP and NP hard. Okay. So this is not right. Okay. Now R is NP hard. Yes, it can be in NP hard because you know that it is not in NP. So as it is not in NP, it is not in P, and obviously it not is in NPC. So R can be NP hard. Okay. Now Q is NP complete. Okay. What about C? So Q is NP complete. In terms of Q, know that Q is not NP, so it is not NP complete. Q is NP hard. Q cannot be a NP hard problem because there is no NP complete problem that is polynomial. So Shreya first gave answer D as a correct, that Q is NP hard. So Q cannot be a NP hard problem because there is no NP complete problem that is polynomial time reducible to Q. Okay, got it? So are you getting that why D is not correct? So B is the right answer. So let's check the answer. Okay. So the question is, if x a problem, so if x be a problem that belong to the class NP, again draw the picture PNP, NP complete, NP hard. Okay. So where x is here, uh, x is here. Okay. Now then which one of the following is true? Okay. So is A correct? There is no polynomial time algo for x. So if x is here, x can be here. Okay. Are you getting it? So the general answer question is, general statement is x be a problem that belongs to a class NP. Okay. So x can be P or x can be NP, because you know that. So you will remember this diagram. Okay. Now your option is that one x is given, so I can write x here. Okay. X is in NP, so this whole is NP. Okay. So x can be anywhere, so this whole is NP. So x can be here, x can be here, x can be here. Got it? So there is no polynomial time algo for x. So you know that if x is here, it means it is a problem of P. So one polynomial time algorithm exists. If B is in, so this is not correct. Now if x can be solved deterministically in polynomial time, then P is equal to NP. Okay. So if x can be solved deterministically, like there is a yes no answer, then in polynomial time, then P is equal to NP. Okay. So uh, so here you can see that this B is also incorrect because x may belong to P. So if it belongs to P, then P not is equal to, if x can be solved deterministically in polynomial time, then P is equal to NP. So if it belongs to P, then it can belong to NP. Okay. So this is also, P cannot be equal to NP. Okay. So this is fine. Now C is correct. Okay. Because if 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 NP complete set is intersection of NP and NP hard. Okay. So it is saying that x is a NP hard, then NP complete. So it is saying that if it is NP hard. Okay. So now it is saying that previously it says that it is here, now it says that it is here also. So it is a combined, so that means it is basically here. Okay. So it is a NP complete problem. Got it? So C is correct. Okay. So now please try to solve this one. So Balaram was right for the previous answer. কোথায় তুমি?
করতে করতে খুবই বোর লাগছিল।
হুম
আমি ঘুরতে বেরিয়েছিলাম, হাঁটতে বেরিয়েছিলাম।
হুম
তবে ফুচকার দোকানটায় গেছিলাম দই ফুচকা খেতে, ও আজকে বসে।
আচ্ছা, তারপর?
তাই সিঙ্গার আমি যে আয়ে ব্যাংক থেকে চালিয়ে সাথে সাথে আসতাম,
হুম
ওখানটায় যদি চিকেন স্টিক খাচ্ছে। আরে এমনই
হুম
আমাকে কাকু এসছে না আজকে,
হুম
তবে খুব খিদে পেয়েছে, পেটে ওটা টকবক করে কোথাও একটা বেরিয়েছিল।
আচ্ছা।
আমার বিদেশের অর্ডার দেওয়া হয়ে গেছে, তারপরে ওরা ফোন করে বলছে কি খাবি। একটা লোকের কথা বলছিল, ওটা খেয়ে নষ্ট হবে না,
হুম
তো ওদের দেওয়া রাতে বিরিয়ানি বলেছিল।
তুমি বিরিয়ানি খাচ্ছ, আমি কি খাবো? তুমি বিরিয়ানি খাচ্ছ, আমারও তো বিরিয়ানি খেতে ইচ্ছা করছে। আমার রাতে খুব বাজে খাবার, পিন্ডি ছোলে, আমি ওটা খেতে পাচ্ছি না। আমি এতক্ষণ ধরে জোম্যাটোই দেখছি, আমি পড়াচ্ছি আর জোম্যাটো দেখছি। আজকে তো আমার আজকে তো আমার ওই এনপিটিএল এর ওটা ছিল না। আচ্ছা খাও, আমি ওদেরকে একটা অ্যান্সার বলে আবার কল করছি। হুম Yes, you are right, Ravi. So basically, click is a NP. So click, what is click? So you must have seen here that I solve this diagram. So one is circuit satisfiability problem. Then so first comes circuit satisfiability problem. This is circuit. Okay. Now come satisfiability problem. Then 3CNF. Then click. Then vertex cover. Then ham cycle. Then traveling salesman problem. Okay. And subset sum. Okay, so if now our question is, if click is an NP complete problem, so click, so it is saying that suppose a polynomial time algorithm is discovered that correctly computes the largest click in a given graph. Okay, so for click it is polynomial time algorithm. So you know, if this is in polynomial, it is also in NP. So click is also P plus NP. Fine. Now, in this scenario, which one of the following represent the correct Venn diagram of the complete complexity class P, NP and NP complete? So we have seen this, we have P, we have NP. We have diagram here already. So you have seen that this is P, this is NP and this is NPC. So NPC is basically NP, NP hard plus NP. So you know this, you know this. So here what becomes? It becomes, now it came P is equal to NP. Okay. So P is equal to NP means P is equal to NP is equal to NPC. So D is the correct option. Okay. So now try to solve this one. Ravi, please try this one also. হয়ে গেছে, তোমার দেখে তো আমার লো পাওয়ার বেড়ে গেল।
আমি হচ্ছে তো ব্যাক করে নিয়েছি,
আহ,
তো কালকে তো খাওয়ার পর তো আজকে ওভার রিডিং হয়ে যাবে বলছে।
হুম
এমনিতে করতে নিলে হাফ রেডি দিবে, তোকে হাফ রেডি করে দিবে।
আমার যে কি খিদে পাচ্ছে, আর তোকে দেখে যে কি
আমারও খুব খিদে পেয়ে গেছে, তুমি অত করে অল্প খাচ্ছি।
जा रहे हो ना आप? जा रहे हो ना, बात कर लो, कोई दिक्कत नहीं है ना, ये पूछ रहा। ठीक ठीक ठीक। हम्म, fine. Let's. So this is a. You have seen in the class that what are the linear problem, and what are the linear constant. You have already like Sarah has uploaded video on that. Okay. So now our question is, we have four equation, and which one of them is, which of the following is a linear constant. Okay. So what is a constant? So like we have a optimization problem, and we have to minimize or maximize something, and we have along with that we have some constant. Okay. So always you know that a linear constant variable should not be multiplied together. Okay. So for instance, this x2 or xy or xyz, this term, okay, cannot be a linear terms. Okay. So now find out where this type of terms are absent. Okay. In which equation this term are absent. Okay. So you say that yz is not linear, xy is not linear, and xyz is not linear. So C is the correct option. So C is a linear constant. Okay. Now try to solve this one. Okay, so let's take that. So the president is arriving to inaugurate a stadium. Okay, so we have a stadium here. He will go directly from airport to the stadium. So here we have airport. He will go directly from airport to stadium. Okay, fine. Security considerations require two routes to be available for president that do not overlap on any section of road. Okay. So one road should be here and one road should be here. They doesn't overlap each other. Okay. Now, now, uh, though the routes can cross each other at intersection. Okay. So it can cross each other at intersection. So what are the two routes? So routes are from here. Okay. Fine. So these are two routes. Okay. Now we have to reach here, from here. This is the starting point and this is the ending point. Okay. Now this can be modeled as a network flow problem where the source and the target are the airport and the stadium road intersection a node and each road as a segment is an edge. The actual flow problem to be solved is to what should be the actual flow problem. So we need two edge disjoint paths from source to destination. So what we need? We need edge disjoint path because you have seen here. So they can this path are disjoint set. Okay. Now, so say source to destination. Okay. So set each edge capacity to 1 and check for a flow of size 2 or more. Okay. So now what you will do? Set each edge capacity as 1. Okay. And check for a flow of size 2. Flow will be of size 2. Okay. So what is the accepted answer? So the accepted answer is assign each edge capacity 1 and check the maximum flow is at least 2. This one. So this is the correct answer. Now we have this problem. Please try to solve this problem.
हेलो मिस्टर सुभान
हम्म
हो गया
नहीं सर और 10 मिनट बस 5 मिनट में ख़त्म करेंगे आज. So Balaram, so I think you are getting email about this. Okay, that there is a weekly log sheet you will be getting where all the videos and all the content link of the contents are provided. So it is available through the YouTube. So the problem is like city authorities are concerned about traffic accidents on major roads. They would like to have ambulances stationed at road intersection to quickly reach the scene. So scene of any accident along this road. Okay, so this is city. Okay, so from each city you go to another city. Fine. So this is a graph of your so this is a graph of your uh, map or graph or map of your city. Fine. Now they would like to have a ambulance station at road intersection to quickly reach the scene of any accident along this road. Okay, so where ambulances will be? Ambulances will be here. Ambulances will be placed here at the road intersection. Got it? Ambulances will be, sorry. Oh, okay. Is there any other intersection? So ambulances are placed here. Okay, where there is a plus sign. Okay. Now, to minimize the response time, ambulances are to be located at intersection with traffic lights so that any segment of road can be reached by at least one ambulance that doesn't have to pass through a traffic light to reach the scene of the accident. So suppose a accident happens here. Okay. So if ambulance is here, it can directly come here without without facing any problem in this traffic lights. So there is, these blues are the traffic lights. Okay, so if a accident happens here, so this is a accident light. Okay, and this is the ambulance. Okay, so are you getting like why this is important, like how ambulances are places at the crossing before the traffic light, so that if any accident happens in any city, it can go directly. Okay, now to minimize the response time, the ambulances are to be located at the intersection of the traffic light. If we model the road network as a graph, okay, where intersection with traffic light at vertices and intersection with the traffic lights are vertices, and edge represents the road segment between traffic lights and graph. The graph theoretic question to be answered is, so now the here they are saying a different thing, like if we model the road network as a graph where intersection with traffic light and vertices. Now see how many vertices we will have. We have three vertices because there are three intersections. Got it? And what are they saying? That vertices and edge represent road segment between traffic light. Okay. Edge. What are the edge represent? Edge represent road segment between the traffic light. So if you name it A, B, C, D, E. Okay, so how many, so and this is W, X, Y, so this is W, X, Y. Okay, now if you see that for for W and X, okay, it is saying that uh, where intersection with traffic lights are vertices and edge represent road segment between traffic lights. Okay, so here you can see W and X, we have a edge here, this one. I am numbering it as 1. Okay, and X and Y, we have a edge here. So this is 2. And between W and Y, we don't have any edge. Then the graph theoretic question to be answered is, so what should be the answer of this question? So here we have to find a minimum. So what we have to do, we have to cover the vertices, we have to cover the traffic line or the junction. So we have to find a minimum vertex cover. Each ambulance covers the adjacent road and all roads are covered in this way. Okay, so here what we have to do, we have to find a maximum size vertex cover. Okay, so C is the correct option. Now this is the question that we have an exponential time algorithm for a problem A. Okay, so A is not in P, so it is not a polynomial time, it is the exponential time problem, and problem A reduces in polynomial time to a problem B. Problem A can be polynomial time reduces to problem B. From this we conclude that So B has a exponential time algorithm. B B doesn't have a exponential time algorithm because B is polynomial time reducible. It is only reducible, not solvable. Okay, and B has an exponential time algorithm. So you can see that A is exponential time algorithm, but it is exponential, but it is reducible to B. Okay, so B is not B is a reduced version of exponent. So B is not a exponential time algorithm. Okay, now a so this reducibility basically transferability of positive action and negative answer. B cannot have a polynomial time algorithm. So exponential, it is reducible from exponential to, so it is basically reducible, not solvable. So it also can be a, it also can have some it also can have a algorithm which is between exponential and between polynomial. Okay, A cannot have a polynomial time algorithm because yes, it is also not correct, because you know that A is already exponential time algorithm. So none of the above are correct. Okay, now suppose SAT reduces to a problem C. You know 3 SAT or K SAT or 2 SAT. So I have seen earlier what is 3 SAT and what is 2 SAT. You know, to claim that C is NP complete, to claim C is NP complete, we additionally need to show that, so SAT reduces to a problem C, SAT problem C, to claim C is NP complete. So to NP complete, it is NP plus NP hard, NP plus NP hard. For 2 SAT, you know it is polynomial type. 3 SAT, you know it is NP. Okay, so what you have to show next? So C is already a NP hard problem. Okay, because why NP hard? Because one problem, one NP problem can be reducible to C, which is already NP known to be NP hard. Okay, so C, so C which is already known to be NP complete. So it is NP hard. So if we only check, there is a checking algorithm for C. If we only check that C is NP or not, then it is it satisfied all the condition. Okay, so this was the last question for today. So thank you everyone for joining. Okay, so I hope you liked the session. So today it was our last class. Okay, so thank you everyone for joining the session, and all the best for your exams. J Harrier is saying what is NP and difference between NP complete and NP hard. Okay, Jay, I think you are little you are late in class, so I have shown that what is NP and what is NP hard. So this is NP and this is NP hard and this is NP complete. Okay, NPH mean NP hard, NPC mean NP complete, and NP means NP. So one thing is P means polynomial time solvable, NP means it is not polynomial time solvable, but one thing is NP hard. NP hard means I have written it 2 times. Like if every problem in NP, so every problem, so if X, you have a problem X here, if X can be solvable, if X, every problem in NP can be polynomial time reducible to a problem A, then A is called NP hard. Okay, so X is reducible to A, so A is NP hard, not, so X is NP it is reducible to a, it is reducible to a, so a is np hard, not x is np hard. Okay, x is not np hard, a is np hard. Got it? If a is both np, if a is both np plus np hard, okay, if you know about, if you know something about a, that is a is already np, then you can say this is np complete. Okay, np hard and np complete. I think you got your answer. So please, like, always remember the diagram. This diagram is very important. So if you remember this only one diagram, I think you will be able to solve many questions. Okay, so thank you everyone for joining the session. Okay, so all the best for your examination. Okay, we will meet later at some point. Okay, thank you everyone. So Balaram, if you join late, so I think you all got an email from the NPTEL about the feedback form and the weekly log sheet. So please fill the feedback form, and on the below of your feedback form, you will be able to get the uh, access of this, like, or please stay here. I'll give you. I don't know, this is edit. So any of these two link should work. Okay, so have you copied the link? Should I end the video, or do you have any other question? So thank you so much everyone for joining. Okay, bye bye bye, have a nice day.